Hi, I'm Frank Hady. I'm an Intel Fellow and the Chief Optane Systems Architect at Intel. It's a pleasure to be with you today to talk about the role of persistent memory in high-performance computing. We'll start off by describing the memory technologies themselves. It's got to be where the storage starts. We'll talk about how those memory technologies fit within the memory and storage hierarchy. And finally, focusing on one in particular, talk about very high performance SSDs and their role in HPC. And finally, persistent memory itself and its role in HPC. What is a memory? The very root of a memory is the physics within which the 0 or the 1 or multiple levels, multiple 0 and 1s are stored. That's really within the materials themselves. Those materials are formed into an electrical component that makes those materials accessible, and it makes it so that we can change the state perhaps of those materials. And then finally those electrical components are put together into a structure that makes many cells readable and writable. We'll talk about three types of memory technology today: DRAM, 3D NAND, and then in the center, 3D XPoint. All very different memory technologies. To show you how different they are, let's talk about their three traits. DRAM and 3D NAND both store data electrostatically. 3D XPoint, actually the first new memory since the 80s, stores a 0 or a 1 in the bulk atomistic properties of the materials that make up the cell. Both DRAM and 3D NAND have a transistor as a part of the cell. DRAM adds to that transistor a very large capacitor, and I'll show you the size of that next. 3D XPoint, on the other hand, really just has a selector and a memory element per cell. It doesn't have a transistor per cell. And then finally, how are they structured? And this makes a big difference in the area, in the density of the memory itself. DRAM is planar. You can't stack DRAM cells within the silicon. For both 3D XPoint and 3D NAND, you can stack them. They're 3D memory cells. Pictured here is a cartoon of a 3D XPoint array. The yellow and the green represent a single cell, the selector and the memory element of that cell. And then you can see the silver bit lines and word lines above and below each cell. The memory is used by accessing the cells, let's say for a read, by biasing a bit line and a word line so that a single cell is enabled. A single cell is turned on for reading. Same is true for writing, although the bias points would be different. You can see now that the XY is defined by the crossing of two metal lines, the bit line and the word line, and there's no transistor per cell. So we can make this array very dense in the X and Y direction, and in fact we can stack the cells to make it dense in the 3D direction as well. So we can define a very dense memory here. So what we just looked at was a cartoon. Here we actually have, by where it says 2DEC, an actual micrograph picture of a cross-section of a 3D XPoint array itself. And then on the left-hand side of that small picture is the CAD drawing, or the colorized drawing of that memory array. You can see how small that memory array is compared to the metal lines above and below. And this array is put in between the metal lines. In 2017, we shipped an SSD with our first 3D XPoint memory. It's called an Optane SSD. That was with 16 gigabyte die. This year, we'll ship 32 gigabyte die, and you can see that we got there by going in the Z dimension. We actually layered two more decks on, doubling the density of the memory itself. So look for that product this year, and we'll talk a little bit more about that one as we go. Let's actually get back to our three types of memory though, because I want to show you the difference in density between these three. It's very important actually to the story of the memory hierarchy. On the left-hand side we have DRAM. We already talked about it being a transistor and a capacitor, and you can see the very large fins coming up. That's the capacitor of the DRAM memory itself. In the middle we have a different rendering, a different cartoon of the 3D XPoint array and of the cell itself on the bottom. And then finally on the right-hand side we have 3D NAND, and you can see again a single cell on the bottom. Now, this is a little bit misleading because it makes all these cells look like they're the same size. You can see that NAND is planar. 3D XPoint and 3D NAND can stack, but the cells look the same size. So if we advance to the next slide and scale things proportionate to real life, you very quickly find that the size of the DRAM cell is very large. Look at the very large capacitor that sits on top of that cell. 3D XPoint itself is much smaller. Inside that circle is a single DRAM cell. Inside that circle is a 3D NAND cell. I'm sorry, a single 3D XPoint cell. And, of course, on the right is a single 3D NAND cell, and now stacked very, very deeply. So you can see 3D NAND has the smallest cell and the deepest stack. DRAM doesn't stack, has by far the largest cell, and then 3D XPoint has a very small cell, not stacking as deeply as 3D NAND. This difference directly corresponds to the difference in capacities that you'll see. Currently, DRAM is shipping 2 gigabytes per die, and as I just showed you this year, we'll ship 3D XPoint at 32 gigabytes per die, and NAND is more dense than that. All right, I'm going to be focusing on this middle memory. I'm going to be focusing on 3D XPoint as our persistent memory and as our fast SSD. Why am I not focusing on 3D NAND? 3D NAND is a storage technology. The accesses are actually quite long. The block sizes for reads and writes are quite large. In fact, the access sizes are so long and the blocks are so big, you really can't access a cache line. You really can't access it like a memory. You need to access it like a storage. DRAM, of course, you can access like a memory. However, it's not persistent, and so it's difficult to make a persistent memory. It's also not nearly as dense as 3D XPoint, so you can't get to the same high capacities that you can get to with 3D XPoint. Now, I will say that there are folks who use DRAM as persistent memory. If you look up NVDIMMs, you'll find that people build DIMMs with NAND on them and with either a supercapacitor or a battery connected to that DIMM. We're not really going to talk about this in this presentation because first, it's relatively expensive. It's as expensive as NAND plus the rest of what I described to support the non-volatility, and it doesn't get you to the high capacities. So while that technology has been around for a long time, it has really a very limited use case. We'll be focusing on 3D XPoint memory. It's in volume production. First memory to be in volume production, first new memory to be in volume production since the 80s. And it has that high capacity and that persistence that we care about for persistent memories. I told you I'd talk about the storage hierarchy, and we really need to see how persistent memory fits within that hierarchy. On the bottom, we have capacity. On the left-hand side, we have bandwidth. I'll warn you that this is not to scale. Neither one is actually to scale. Because if I drew it to scale, it actually ends up looking mostly empty. It's amazing what we've been able to do with the memory and storage hierarchy. At the very top on the left, we have the compute cache. Small but very, very fast. Very low latency, very high bandwidth. We have in-package memory in some cases. Think of like an HBM memory sitting directly underneath the compute cache as a very high bandwidth memory resource. And then we have memory itself, DRAM, the main memory of the system, built out of that DRAM technology that I described. And then we have 3D NAND flash as an SSD, providing a huge capacity. And then finally, we may have a tertiary storage made out of a hard disk drive. Many systems still do include that as the lowest cost per bit technology. Notice I have not put persistent memory in here yet. And in fact, I want to show you what's been happening in the memory and storage hierarchy that really calls for the need for persistent memory, both because of its capacity and because of its persistence. And the story really starts back in about 2004. In about 2004, we had come off the end of Dennard scaling. And so instead of making cores that were faster and faster and faster, we, the industry, started making multi-core processors. Interestingly, back to that hierarchy that I showed you on the last slide, each of these cores may well be running its own operating system in a virtual machine. So each of these cores really needs its own storage and memory hierarchy. And that's what I show you on the right-hand side. That hierarchy that I described really has to be provided for each of these cores. But you know that there's actually only one set of physical memories outside of these processors. And so that set of physical memories has to satisfy all of the cores at the same time. Let's see the impact that that has. And the best way to see the impact that it has over time is actually to go back to the memories themselves and look at how they're scaling over time versus how multi-core processors are scaling over time. And so the chart that you see here has time on the x-axis in years. On the left axis, on the y-axis, but the left axis, you see bit count per die. And we've graphed DRAM in the green triangles, and we've also graphed NAND in the blue circles, and then you can see 3D XPoint in the red crosses coming in. And what you find is that DRAM scaling has actually slowed recently. It's not going at the historical rate that it used to. NAND scaling is still going very quickly. In fact, NAND is actually scaling faster than the extra data that we're putting in, that 2x every 3 years you hear all the time. NAND is scaling faster than that and is able to store more of the data. Story for a different day. Notice the purple boxes, which correspond to the core counts on the right-hand side axis. Notice how rapidly that's increasing. Core counts are actually increasing very rapidly. And more to the point, each of those cores, since it needs its own hierarchy, likely needs more than a gigabyte of memory. Many instances when you go look at cloud service providers and the DRAM per instance, or when you think about HPC, the capacity is, say 4 gigabytes per instance, and so the slope of demand for each of those cores at 4 gigabytes is significantly higher than DRAM is able to provide. What this means is we end up with a gap in our hierarchy. We find that the memory capacity is falling short of what we want it to be for these multi-core processors. In fact, that is exactly the gap that persistent memory needs to fill. It's not the only gap in our, but that was just one level in our hierarchy that's missing. Let's look at another one. And this one involves NAND and NAND-based SSDs. NAND capacity has been increasing at a very rapid rate. NAND density has been increasing at a very rapid rate. But throughput has not been increasing as rapidly. What that means is what you see in this chart. Again, it's time on the x-axis. This time on the y-axis, we have performance per terabyte. It's write throughput per terabyte. Interestingly, over the last 20 years, write throughput per terabyte of NAND at the component level, and therefore at the SSD level, has significantly decreased. What this means is that some of the data that we want to access in SSDs is stranded from a performance point of view. And we end up with another gap in our hierarchy. We have SSDs which aren't as high performing as we wish they were. And then finally, we find that accelerators join the hierarchy. And very interestingly, accelerators for a long time have been asking for very high bandwidths. And I think conventional wisdom is that when you have an AI accelerator, it's all about bandwidth. But one of the things that's changing as we go forward in time is we're starting to see larger and larger models and larger data sets that operate on those models. And what that's meaning is we're starting to get a couple of different gaps in our hierarchy. One is that bandwidth demand that I talked about for accelerators, and that's really driving this need for in-package memory. We're stacking SRAMs called the Rambo cache to provide that. We're including HBMs in products to provide that bandwidth at a higher capacity. However, I think we're also coming to a time where we're going to say the capacity even the DRAM provides isn't enough for some of these models, and that's why I've colored that region yellow that I added before. I think these new accelerators add to the urgency for that higher capacity memory layer, and that's one that really persistent memory fills well, and we'll talk about that. Let's take a little bit different view of the memory and storage hierarchy. We'll go back to that multi-core processor that we talked about. You see it here. We'll also add that XPU, that accelerator that I was talking about on the last slide. But think about the logical hierarchy that each of these really has below it. Each one of them has their own SRAM cache. They have their own view of DRAM, even though the DRAM on the platform is shared. They have their own view of 3D crosspoint. We'll be calling that persistent memory next, even though that's a shared resource. And they may have an in-package memory. Often in the data center or often in the HPC installation, there's a gap now. And across that gap, across the network, we find storage. Storage built out of perhaps NAND, of course, built out of hard disk drives maybe, and increasingly, as I'll show you, built out of a 3D crosspoint layer. Very complicated memory and storage hierarchy for a multi-core processor, and one that is very demanding on the hierarchy. We're going to simplify this as we walk through the hierarchy to make it easier to talk about. And in fact, we'll show you just this one triangle so that you know where we are, or this one pyramid so that you know where we are. But I want you to understand that it's that complex interaction that sits behind this pyramid. And I'm going to focus on two gaps within this pyramid. They correspond to the gaps that I showed you in the hierarchy before. We'll talk about that capacity gap. That's the persistent memory gap. And we'll talk about the storage performance gap. That's that fast storage gap. And interestingly, if you look at the latencies and the capacities on the right-hand side, you can clearly see that if you want to change one order of magnitude in each as you go from level to level, that we really do have those gaps. It's one way of showing that they exist, of course. Of course, there's others. All right. Let's look first at that performance storage gap that I described. And I'll tell you that 3D crosspoint as a technology is being shipped today in Optane SSDs. You could see pictures of them on the left-hand side there in two different form factors. But I think the important chart to show is actually the one on the bottom right-hand side. This is a latency at load plot, and it really shows you the difference between a NAND SSD and between this high-performing SSD. And this is a good lead into showing you how this high-performing SSD makes sense in HPC, or examples of where it makes sense. So the x-axis now is IOs per second. That's for a read-write workload, a 70% read, 30% write workload, 4K byte accesses randomly addressed. So it's that classic heavy workload for storage. And then on the y-axis, we're showing you the average latency of the reads for that particular throughput that you see on the x-axis. This is called a latency at load plot, and it's a great way to show performance at different loads in a system. Notice that blue line there, the blue line going across, that's actually our first generation Optane SSD. The dotted green line is a contemporary to that one, NAND SSD. Notice they're a factor of 10 difference in latency. So it's a 10x difference in latency. The Optane SSD is about 10 microseconds, a little bit less. A NAND SSD, because of the intrinsic media it has, is more like 100 microseconds away for that read. Notice also that the Optane SSD is able to stay very flat as the performance, as the throughput is increased, while NAND SSDs, any NAND SSD, the latency goes up as the throughput is increased. I don't have the other lines that I could put on here. You can actually plot percentile lines on a chart like this. I do that sometimes. And what you find is that for less frequent IOs, for that long tail, that Optane SSDs, actually 3D crosspoint based SSDs, do much better than NAND SSDs. We call that quality of service. Is it always low latency, or is it sometimes high latency? It's another place where Optane SSDs shine, and that's important in the usage models. Now, there is a dotted gold line underneath that blue line. That's actually an early look at our second generation SSD. That one will ship this year, and so keep watching and you'll see where that line actually ends. I'm super excited about it. It really shows you what 3D crosspoint is able to do in an SSD, and it's based off that second generation 3D crosspoint technology I told you about. It's called ADS. That's for Alderstream. That's the code name for that second generation SSD. Okay, the important thing to take away from this is 1/10 the latency and much better quality of service. The Optane SSD also has a much better endurance, 60 drive writes per day, and it has a few other advantages that change the way in which it can be used for HPC. One of the things you have to think about when you're doing storage is what's the software overhead. And the chart that I have in the middle is a software stack diagram for accessing an SSD. The application is on the top, so that would be your HPC application. And then as you're accessing storage, you either map it directly as a block device, the standard raw device access, or you map it through a standard file API into a file system and have the file system manage that file for you. There you hit a generic NVMe driver. NVMe is a new protocol, relatively new in the last 10 years, that was developed for SSDs specifically and really helps get to low latency for Optane SSDs. This technology as an SSD gives you the opportunity to access it as storage. That means you ask the operating system to open a file, and then you do a read or a write through that operating system to storage. That's a particular usage model that much software is written to. Shipping 3D XPoint as an SSD means that software has access to that technology. And notice I've marked the OS stack latency. Each access to this memory has to go through the operating system, and there's overhead in doing that. Next, I'll talk about how much overhead that is. This is a key difference between an SSD and persistent memory. I'll show you later that persistent memory doesn't have that overhead. Okay, so the same stack diagram in the middle. On the left-hand side, you can see something called the SPDK, the Storage Performance Developer Kit. This is software written actually by Intel and made available to everybody open source. And you can see actually that they're able to get over 10 million storage IOs per second from a single thread. That means from a single CPU, they're able to get that many IOs. That's a shockingly high number. And what the Storage Performance Toolkit allows you to do is to shortcut that stack diagram that I showed you on the right-hand side, take that generic NVMe driver, move it up into user space, and now you don't have to go through the operating system to get to the SSD. It's one example of a way to get to the SSD, a very fast SSD with much lower latency and much lower overhead. You may not want to execute everything from user space. On the right-hand side is an example of Linux itself getting much better, getting much more efficient at accessing high-performance SSDs themselves. This is a post from Jens Axbo. He's the longtime storage kernel maintainer for Linux, and he built a very interesting new capability called IOU ring. A great thing to go read about. And what he's able to do is to get the kind of performance that you see on the bottom, which he posted on top of actually an Alderstream early version that we're able to get him. And notice he was able to get 2.5 million IOPS from a single core to a single drive. On the left-hand side, we actually had multiple first-generation Optane SSDs. And notice the latency, 3.4 microseconds is the average latency. I can tell you very little of that is software. So there are ways to get to an SSD. It's still not as fast as persistent memory. Keep that 3.4 microseconds in mind. There are ways to get to an SSD, an Optane SSD, with very low latency. I wanted to make sure you knew that. Okay, let's talk about usage models that are relevant to HPC for fast storage. And I'm going to go ahead and build this one out. There's two examples here, but they have a certain commonality that I really want to get across. On the left-hand side, we have VMware vSAN. This is a really interesting solution from VMware, which allows an enterprise which has systems with compute and storage around the enterprise to manage that storage as a single resource, a single combined resource available to that compute, which is distributed around the enterprise. And the interesting thing about this is vSAN now includes both NAND storage and 3D XPoint storage, Optane storage, and it uses them very differently. The Optane storage is actually kept locally, and so when an application and local, by that I mean local to the compute. So when an application does a write, that write goes first to that Optane SSD. If the application were to read that data again quickly, that read would come from that local SSD, even though that local SSD is managed as a part of the global resource. From that local Optane SSD, those writes can then trickle out at the rate that's allowed by the network to the NAND storage that's across the enterprise for permanent storage. And so you see a model. The model is the first write goes very quickly to an Optane SSD, but the bulk store is in the NAND SSD. Same model with a little bit more is used on the right-hand side. Very interesting new company called VAST. And they have a storage solution that provides very, very large storage, again with this two-tiered approach. For VAST, though, both the Optane storage and the NAND storage are across the network. And I have seen uses of VAST in HPC. If you look at the literature, you'll see some of them. Very interesting the way they're using this two-tier. Writes that come over the network are immediately written into the Optane SSD, the one built from 3D XPoint, and those writes can commit very quickly, allowing the commit to go back over the network, calling it done, because it is. But then as data is collected in those Optane SSDs, it can then be deduplicated, it can then be compressed, and then stored across the NAND SSDs, which sit in the same appliance that they're creating. And by doing this, they get very high performance from the Optane SSDs and then from the NAND SSDs, and they've gone to a 4-bit per cell QLC technology. They're able to get very, very high capacity because of the technology, because of the compression, because of the dedupe. Great combination of using those two for those two types of SSD technologies. And what I want you to get from this slide is when you think about using storage or doing storage in HPC, think about those two layers and think about how you can use this very fast storage as a commit point, as a log file, and then be able to more efficiently take that data and move it into longer term storage in NAND. We see that over and over again. What other HPC usages might make sense? I think checkpointing could very much make sense. Checkpointing has to be done very quickly and maybe even more to the point, and I would checkpoint, I think, to a local Optane SSD, not over the network, so that all of the nodes in an HPC system can checkpoint at the same time without swamping the network. Importantly, for an Optane SSD, it allows for 60 drive writes per day. That's how we measure endurance in SSDs. And to calibrate you, the highest endurance NAND SSDs tend to allow 3 drive writes per day. And so at that's a 20x advantage for the Optane SSD. What that means is if you checkpoint a lot, you won't burn out these SSDs. You don't have to buy capacity just to get extra endurance. You can just keep writing to them. You'll also find that you get higher write performance, so you'll spend less time checkpointing, and the write performance will always be high. Even if you didn't buy a really big Optane SSD, even smaller Optane SSDs have very high write performance because of the intrinsic properties of the underlying memory. And of course, it maintains its write performance as lots of streams, maybe from multi-core processors, checkpoint at the same time. And that's important because NAND actually wants bigger blocks for writes. Optane doesn't care. Another possible use for HPC would be memory expansion. And here, what if the DRAM that you have in the system isn't quite large enough? Well, classically what we would do in computing systems is we would use virtual memory and we would swap in data that was stored in storage into memory, pulling some of the memory image out and putting it into storage. Takes a long time. There is operating system overhead for this. If you're waiting 100 microseconds from a NAND SSD for that data, it's not something you want to do. I think in some cases waiting less than 10 microseconds to get this data, this 4K of data from an Optane SSD makes sense. It's something that it might be worth thinking about. I do also want to say that quality of service that I discussed really matters here because you really don't want to have to wait a long time, a lot longer than 100 microseconds. You don't want to have to wait milliseconds for data to come in. So checkpointing and memory expansion are two interesting potential HPC uses for this very fast SSD. All right. Now we're going to move on to persistent memory. We filled that performance storage layer in our hierarchy. So notice I talked about that gap before, and now it's filled in by that purple box. We still have a box to the left of that, the persistent memory hole, that we have to fill in our hierarchy, and we'll move on to that one next. Okay, so we're talking about the persistent memory layer. You can see that the picture there of the form factor looks very different, actually. And what we're showing there is this persistent memory comes in a DIMM form factor. It is accessed like DRAM. It has a DRAM in-system form factor. This particular solution, we offer 128 gigabytes, 256 gigabytes, and 512 gigabytes per DIMM. Notice those are very large DIMMs, and in fact, you can populate up to 4.5 terabytes of persistent memory per single platform. So it's very high, per socket actually, very, very high capacity, much higher than you could get with DRAM. And so in that chart that I showed you before, we said we needed more capacity. This is how we get it. The memory itself is much more dense than DRAM, and so we can deliver a much higher capacity per platform. How about performance? And I've taken the same chart, that same latency at load chart that I showed you before, and I've added a line to it. So the blue and the green are the same as the blue and the green that I showed you before. The blue is the Optane SSD, the green is the NAND SSD. Now I've added the red line, and the red line is persistent memory. So it is Optane persistent memory built out of that same 3D cross-point memory that I described in the beginning. Notice the latency is much lower. There's no operating system in the way anymore. I'll talk about that a little bit. And so the latencies we're able to attain are very, very low. And in fact, we can get to a pretty high bandwidth too, above 5 gigabytes per second. And in fact, our second generation, which I haven't plotted here, has a higher bandwidth than that. And notice how flat that curve is. So the low latency is maintained even as we go out to higher loads. I should say the red line is actually not 4K reads and writes, it's 256 byte reads and writes, because it's not storage, it's memory. And so 256 byte is a reasonable amount to plot there. Had we plotted 64 bytes, the throughput would be a little bit lower. A story for another day. Let's look under the hood of that DIMM that I showed you on the previous slide. And with the heat spreaders removed, you can see the components underneath. First off, I'd like to call out the fact that there are actually 11 packages of 3D cross-point memory itself. Those are read or written in parallel. It's not like a NAND SSD where you read or write one of them and different IOs go to different devices. Here we actually read them and write them in parallel for a single access. That's part of how we get performance. This thing is really architected from the ground up for low latency and for high throughput. That big ASIC you see in the middle there is actually the control ASIC. It's really the heart and soul of this DIMM. I guess the memory is the soul. This is the heart. And you could see a blow up of what's inside that memory. That is the memory that's responsible for managing the media, for taking for connecting the media also to the system. On the system side, then, you actually have a DDR-T connection, a transactional memory connection to the Xeon processor itself. The Xeon processor, we've had to make a number of modifications there in order to allow it to access that memory channel. It really is a systems integration job to put persistent memory into a system. And what you see on this chart is really a representation of a full systems design in order to make persistent memory happen. Wanted to give you a little bit of background on that. Let's move on. Okay, how does it work though? If you were going to use this in HPC, what do you need to know? Very basically, there's two operational modes. And we have one on the left and one on the right. One is volatile. In other words, when the power is turned off, you'll lose your data. On the right-hand side is the non-volatile usage model. And when I say persistent memory, I really mean both of these, although arguably it should only be the right one where the memory is persistent. Either one gives you the very high capacity of Optane persistent memory. Only the right-hand side gives you the persistence through power fail. Let's go through them really quickly. And I'm going to start on the right-hand side because it's the easiest. In the right-hand side, you have both DRAM and persistent memory. And I've used a picture of the DIMM here, actually one with a different color heat spreader. And what you find is that from the core, you actually have a choice of two different memory address ranges to access. And you, as the programmer, when you do a malloc, would decide if you wanted DRAM as a part of that malloc or if you wanted to map persistent memory itself as a part of that malloc. And you, as a programmer, might well be aware of the performance and the capacity differences, and you could make the best decisions as to how to use these two. And of course, the program may copy from one to the other if desired. But the main point is you're accessing the persistent memory directly. You do go through the system caches, yes, but you don't go through DRAM on the way to persistent memory. And if you were to, and we'll talk a little bit about this later, but if you really want to keep persistence in a power fail, you have to make sure the data is flushed out of those caches to persistent memory. And there's a fair amount of software to use there, and I'll talk about that in the next slide. On the left-hand side is the I don't want to change my code and I'm not going to get the value of persistence way of using this. You do get the value of very high capacity memory. This is a one that we call actually memory mode. I should say on the right-hand side it was called app direct mode. On the left-hand side it's called memory mode. In this case, data is actually pulled from the DIMM into the DDR4 memory, which is managed as a cache. So it's managed as the last level cache, as the LLC. A very large cache, of course, so it can hold a very large working set. The software sees a single memory image that includes both what's in DDR4 and what's in persistent memory itself. So the real memory image on the left-hand side in memory mode is stored in persistent memory, but it's often used out of DRAM. That's very much like the hierarchy that you're used to, so you get the high capacity without having to change any code to optimize for persistence or without having to really understand that there's a separate memory space. Okay, those are the two operating. In the center of this slide is a software stack diagram, much like the software stack diagram that I showed you when I was talking about the SSD, but in this case it's for persistent memory. Now when you use persistent memory, the first thing you would do at PowerUp is map some of that persistent memory with what's called a naming layer, a thin naming layer that PMware file system is used to understanding. And so it can find the data for you. You could continue to use that PMemory aware file system if you wanted to access persistent memory like storage. However, you'd be going through the operating system for every access. That's not really the best way to access persistent memory. You really want to use that direct path that you see right in the middle of the slide, to the right of the PMemAware file system. Now you're able to access persistent memory with load store operations from the core itself. Not read-write like storage, but load store like memory. That means there's no software delay in the path for accessing persistent memory. That's a big deal. That gives you the lowest latency. It gives you the highest performance. If you look at the left-hand side, we have a stack diagram for latencies on the y-axis. It's not labeled, I apologize. And we've split between the hardware and the software latencies. And this is really more of a cartoon than an exact diagram that you see with these various technologies. A NAND SSD, as I showed you before, is about 80 microseconds. I think it was about 100 in my latency at load plot. If you look at an Optane SSD, it's less than 10 microseconds. And in fact, I showed you that our friend Jens was able to access it in just about 4 microseconds, which was super fast. He did it actually by shrinking that green region that you see there, that software latency. But there still was a software latency. And if you finally then make it all the way to the right, you're over to persistent memory. We're doing load store instead of the read-write we did for storage, and that means we're not going through any software to access this memory. We're able to get to persistent memory in this instantiation at about 340 nanoseconds if it's not in the DRAM cache. If it is in the DRAM cache, the access will be more like 100 nanoseconds. That's really fast access for persistence in the system. There hasn't been anything like that before. That is really revolutionary. Now, I did talk a little bit before about extra software work you have to do for persistence to make sure the caches are flushed. If you want to go deeper into this, I would encourage you to look into something called the Persistent Memory Developer Kit, PMDK. It's listed on the right-hand side along with its URL. This is a library, and you can see it in the middle stack diagram that can be used to take care of much of that for you. It is something the programmer needs to be aware of. PMDK is a great way to do that so that you can take advantage of persistence and truly use persistent memory. This means, with the addition of persistent memory, that we've fixed this hierarchy. And so you can see that new persistent memory layer. And notice how it fits right in between memory and storage. It has a much higher capacity than memory. It has a much higher performance than storage. It fits right into that gap. And so let's now talk about how that persistent memory is actually used within the system. And I'm going to go through a number of examples and then have a few ideas for how one could use it in HPC where I don't have a fantastic example. And I'm sure there are many more, and I really encourage you to think about it. The first one I want to go through is a really interesting usage by Oracle. Oracle took their Exadata product, and it's a high-capacity OLTP and analytics system that they sell, and they modified it really from the ground up to use persistent memory. And the diagram on the left-hand side really shows you how they're doing this. If you're on a compute server and you're running this online transaction processing, there will be something that you need to commit, and that's a very important piece of data, maybe a banking transaction that you need to commit. The way they commit that is with a remote DMA over the network, RDMA. Actually, RDMA is a very popular way of using network-based storage. They're doing a RDMA write. That RDMA write in this new Exadata system will actually get committed in persistent memory across the network. The compute server is in one place, the storage server is in another. It'll get committed into the persistent memory very quickly, and that storage server can then reply and say that the write is complete. Then later, that data can be pulled out of the persistent memory and it can be flushed to either an SSD or to a hard disk drive. There's a lot of really good things about using an RDMA directly to persistent memory to get this work done. First, there's no storage stack on the storage server to get in the way. And so that RDMA can complete through hardware means directly into memory. That significantly decreases the latency, and it decreases the load on the processors in the storage server. Secondly, the RDMA doesn't actually have to be a full storage sector size, either 512 bytes in most systems. 4K in some is the native size and the minimum size that can be allocated. I'll talk a little bit more about that later. Both of those mean that the system is significantly sped up. And if you look at the right-hand side, you can see the kind of advantages they're getting. In terms of latency, that RDMA is able to commit 10x faster. So they get 1/10 the latency, a much better latency on this rewrite of Exadata based on persistent memory. And in fact, because of the overhead reduction that I was talking about, they get 2.5x the IOPS. So that storage server can do 2.5 times the IOs that it could do before. So a great success story. There's a really good, I included the URL here, there's a really good walkthrough of how they re-architected the system. A lot to learn from this example. I encourage you to watch that one. You know, a place where we're really finding persistent memory being used in HPC, this is a good HPC example, and I've got 2 slides on this, is around the way that storage is created within the HPC space. And this particular one is something called Deos, but let me start with the problem. The problem is you have an HPC application, and through I/O middleware, you're writing to POSIX blocks, and so you're writing to those 512 byte sectors. The blocks you see in the middle come through in a serialized POSIX file, but there's a whole bunch of serialized POSIX files coming through. Those are the different colors, and they all get intermixed. And when those then get committed to something that is block-based, we find that there are gaps. And so we only use some of the blocks. Say if we're 4K block based on the right-hand side, some of those 4Ks will be full, but many of them won't be because they're at the beginning or the end of that serialized stream of data. That causes our storage to be less efficient and that we waste bytes, but it also causes it to be less performing because those bytes that we waste, we still had to access. They just didn't count in our throughput. On the bottom is a similar example where we have an AI or analytics application, and here it's actually based on objects. And as those objects come through, they can be even smaller than those things that were based on POSIX. And what we find is that we get smaller objects and we get even less efficient use. And so this mapping of the data structures we have in HPC into these POSIX blocks causes these inefficiencies. And that's something that we can address with persistent memory. And it's being done through something called DAOS, the Distributed Asynchronous Object Storage file system. It's not a file system, it's a system. And what I'm showing you on the left-hand side is that conventional storage system that I was describing before. And then in purple, we have the DAOS system. And in the DAOS system, as those writes come in, as that data comes in, DAOS is capable of separating the data by its type. And so if it's metadata, which tends to be very small, if it's a low latency I/O, something you need to complete very quickly, or if it's an index that you're creating and that will need to be read very quickly to provide a result, that kind of thing is placed into persistent memory. These data structures tend to be small and they tend to be very performance sensitive to the application. Those are put in persistent memory. The bulk data, the big blocks that we get, are placed into the NAND SSD like they were on the left-hand side. But by splitting out those small data structures, we're able to be much more efficient on the SSD itself. DAOS actually is very fast. And in fact, there's a 10-node challenge that happens within the HPC space. And DAOS-based systems were 3 of the top 10 in the latest set of 10-node challenges. And on the right-hand side, you can see that mapping of the small data structures, the keys in this case for object storage, into the persistent memory. And then from there, we can point to the bigger objects in the SSD. So for your storage in HPC space, look up DAOS. It's open source. I think it might be very useful to you. It's also a great example of how we're using persistent memory for the small objects, for the high performance objects, and then we're able to use SSDs or even hard drives for the big bulk data store. That's a familiar story you're hearing from me, and it's why I like to talk about this in layers of the hierarchy. These layers really do play together in many of the solutions that you'll see, and you need to think about all of the layers together. How about other high capacity and persistent use cases, other use cases for persistent memory in HPC? I think checkpointing is an interesting one. And essentially what you want to do in checkpointing is you want each of your HPC nodes to be able to write out its memory state periodically, and to be able to do this in parallel with no network traffic, so that if you run into a problem, maybe a power fail, maybe software goes off into the weeds, you can roll back the whole machine to that last checkpoint, start from there. You don't have to start the workload from the beginning. Optane and persistent memory, actually Optane as an SSD or as persistent memory, is very good for this. I described it already for an SSD, and the reason it's good is the same here. The endurance is very high, and so you can write to the same memory many times without burning it out. In this case, you actually don't even have to traverse the storage stack. So one could imagine doing a memory-to-memory copy here in order to do checkpointing, and I'll show you another way to do it that's very interesting on the next slide. Memory expansion is another, I think, clear case here, and I'm going to show you one on the next 2 slides actually, where obviously Optane persistent memory has a much larger capacity than DRAM. And so if you need high local memory capacity, not at the same bandwidth as DRAM, but at a lower bandwidth, so you can build a hierarchy of working sets, then Optane persistent memory is a great solution for you because it gives you that high capacity at a reasonable cost. and it gives you that high capacity in a way that allows the finer-grained accesses of accessing it as memory and allows the no OS overhead of accessing it as memory. There's a really good example, actually, of both of these on the next. And it's from a very new company called MemVerge. And what they've actually done is they've built this piece of software called the memory machine. And the memory machine, you can think of it as almost virtualization for memory. And what they're able to do is to provide accesses, I guess that's that memory hypervisor. They're able to provide accesses to DRAM or persistent memory, kind of like the caching that I showed you in the previous, in the memory mode usage here. But they're doing it in software. And they're able to do it in a way that gives them some advantages here. First of all, doing it in software means that they can carefully manage persistent memory versus DRAM based off of knowledge of the application itself, rather than quickly doing it in the hardware in a cache controller. And interestingly, it also means that they could maybe do this at a system level instead of at a single node level. Finally, it gives them this zero I/O snapshot, that's what they call it, which is very interesting. You guys are familiar with virtualization, that you can essentially create a new virtual machine by referencing an old one and then only taking the new writes to the storage of that new virtual machine and storing those as an incremental update to the old virtual machine. You can do the same thing with memory here, and MemVerge allows this. So in their case, they can actually get a snapshot of memory without even doing the copy, which is super interesting. Check out MemVerge if you want large memory in HPC. Visualization is another place where I think the large capacity memory is really going to matter. And I saw, as I looked around for content for this talk, a number of places where it was starting to be used in HPC. But there's a really, really good explanation of how this works from a workstation perspective. And of course, visualization matters on the workstation too. And it's at the link down here. It's from SideFX Houdini folks, the folks who build the animation software that you use. And they did a very interesting thing. They had essentially a physics simulation of a volcano and of the plume coming out of a volcano, and they ran it on a number of different systems and mapped out the time and mapped out what was going on in terms of memory accesses. And what they found was all the way on the left-hand side where they had 64 gigabytes, the little b means bytes in this case, it's not right, but that's the way it is, that they ran out of memory fairly early into the simulation. With 64 gigabytes on Linux, they were able to better use that memory, but they still ran out of memory. They had a different system in there, which is the 64 gigabytes plus the 512 gigabytes. This was actually a Xeon-based workstation, and they were able to put persistent memory in. And when they do that, they find that they can, on Windows, run for longer. And this is a fairly old, this is a couple years old, so I think that Windows one might have changed now. But the example I really wanted to get to was the right-hand side, where they were able to run the simulation for much, much, much longer and at reasonable performance, because the capacity that they had in the system was the 64 gigs plus the 512 gigs. That meant they could run this visualization longer. If you have a big visualization workload, it has a very large memory image. Maybe you're collecting over time and you want to be able to go back and forth in that time, in that visualization. Think about persistent memory as a solution for that. And I encourage you to watch the video here. Let's talk about one last potential usage model in HPC. I say potential, I haven't really seen this happening yet, but it seems to me like it might be coming. Really interesting paper by some folks at Facebook on the right-hand side. And the point that they make in this paper, and you can see some of it in this graph, is that recommendation models are very important in the real world, and that these recommendation models are not often what's focused on in AI research and in AI workload characterization. And further, that these recommendation models have a very different compute to memory capacity ratio than one sees in things like ResNet, which are often the focus of that work. In fact, their compute to memory capacity ratio is much lower, meaning they need more memory for the same amount of compute. And some of these workloads, say graph neural networks, are growing very large in size. And you can see that on the left-hand side. That's actually the chart that I already showed you earlier in the presentation. Taking these two together, you could easily come to the conclusion that in HPC we will see AI workloads where very large capacity is needed per node, and that capacity doesn't always have to be as high performing as HBM or even DRAM. There would be working sets within these AI workloads themselves. If you find that happening, I think you'll find that persistent memory and the large capacity that it allows is a great match for those AI workloads. So watch for this. I think this is a coming trend, and perhaps you'll see that it is. And we've reached the end of the presentation. 3D XPoint really is the first new memory technology in decades, and it is the memory technology which allows us to do very fast SSDs, Optane SSDs, very low latency, very high performance, and most importantly for this presentation, to make persistent memory happen. Load store accessed, high capacity, and persistent across power fails. It really is a fundamentally new memory technology, a fundamental new technology for the platform. I think there's tons of opportunity to use this in HPC to speed computation. There's an opportunity to relook at the algorithms that we're using in HPC based off of big memory, based off of persistent memory. I encourage you to go look at those. Hopefully this talk has given you a starting point for that. And boy, I'd love to hear about what you see persistent memory can do for you in HPC. Drop me an email. Let's talk about it. It'd be great. Thank you for your time. I hope you enjoyed this presentation. Have a great IEDM.